right, so picking up where we left off, we're still going to be taking a look at L'Hopital's rule. So we're going to look at example 5 here from the book. This one wants us to evaluate limit as x approaches 0. And they give us e to the x minus 1, all that over cosine of x minus 1. So when we get started on this, we're going to try to evaluate this limit. We get e to the 0 is 1, minus 0 minus 1, all that over cosine of 0 is 1 minus 1. So this is our 0 over 0 form again. So we're in this nice indeterminate form here, so we're able to use L'Hopital's rule. So use L'Hopital's rule. Oops, spell it right. And this basically says I can take the limit evaluated at the same place, and I take the derivative of the top, which e to the x is its own derivative. Negative x has derivative negative 1. Negative 1 has derivative 0, so we don't write it. And the derivative of the bottom, cosine of x has derivative negative sine of x. And minus 1 is going to drop. So we get down to here, and we'll say, all right, let's reevaluate and see what happens. I get e to the 0, which is 1, so the top becomes 1 minus 1 over sine of 0. Sorry, negative sine of 0. 1 minus 1 is 0 over sine of 0 is 0, negative 0 is 0, so we're still in 0 over 0 form. So when that happens, or you're still in an indeterminate form, you can use L'Hopital's rule again. So we're going to use L'Hopital's rule a second time. Limit is still as x approaches 0. The derivative of the top, e to the x is e to the x. The minus 1 drops. Negative sine of x has derivative negative cosine of x. So now when we substitute 0 in, e to the 0 is 1 over negative cosine of 0. So that's 1 over cosine of 0 is 1, so that's 1 over negative 1 is negative 1. And we finally are able to get our limit after using L'Hopital's rule twice. If you didn't end up in an indeterminate form like this again, so like if I did this and I got 7 over 5 or something, then I don't apply L'Hopital's rule the second time. That's only if I'm in my indeterminate form, and so I got my indeterminate form there, and then just I needed to apply my indeterminate form again, and then I eventually got everything to work out. Okay, so moving along, we're going to do a couple more of these. So for example 6, they give us a limit as x approaches 1 of x squared plus 1 over 2x plus 1. So we're going to try to evaluate the limit. I put 1 up here. I get 1 squared plus 1. Down here when I put 1 in, I get 2 plus 1. And this is just going to equal 2 over 3. So this is not an indeterminate form. We just, actually, as we just tried to evaluate the limit, we were able to evaluate it directly. So that's your answer. You don't use L'Hopital's rule on this one because you're not in that 0 over 0 form. So this time we didn't need it, so we're done. There's no L'Hopital's rule. We didn't get 0 over 0 or infinity over infinity, or a indeterminate form we were able to convert over. So let's look at a couple more where you can get them evaluated. We're going to look at limit as x approaches 0 of 1 over sine of x minus 1 over x. So when we evaluate this one, 1 over 0, or let's see, sine of 0 is 0, so 1 over 0 becomes like an infinity minus, as x gets close to 0 here, that's an infinity. So we're in this form infinity minus infinity, which is indeterminate. We need to get the form, we need to algebraically get it to like 0 over 0 or infinity over infinity. And the way we're going to approach this one is we're going to find the LCD. So I'm going to multiply this by x over x, and this one I'm going to multiply by sine of x over sine of x, and try to get this thing to, try to get this where we can compare it and get it as a nice division. So we get limit as x approaches 0. We haven't applied L'Hopital's rule yet. We're still trying to get one of the two forms that lets us apply it. We have x minus sine of x up top. So 1 times x is x, 1 times sine of x is sine of x, and the denominator is sine of x times an x. So we'll say x sine of x. When I put 0 up here, I get 0 minus sine of 0 is 0. When I get 0 down here, I get 0 times sine of 0, which is 0. So I get 0 times 0, which is 0. So we're in the form 0 over 0 now, so we can apply L'Hopital's rule. So now that we have the correct form, we can use L'Hopital's rule. Derivative of x is 1. Derivative of negative sine is negative cosine. We have to use the product rule down here. I'm going to leave the x alone and take the derivative of sine. So x left alone. Derivative of sine is cosine. Plus, now when I take the derivative of x, that's 1, and I leave the sine alone. 1 times sine of x is just sine of x. Okay. So I'm going to put zeros in this again. I get 1 minus 1 up top, which is 0, over down here I get 0 times cosine of 0 is 1, so I get 0 times 1, which is 0, plus 0, so I get 0 over 0 again. So I'm still in form 0 over 0. I don't see anything that cancels, so it looks like I'm going to have to go through and use L'Hopital's rule a second time. Let's see. It means L'Hopital's rule again. So derivative of 1 is 0, so it goes away. Derivative of negative, so cosine has derivative negative sine. So we get minus negative sine up top. Down here we got to use the product rule again because I have x times cosine of x, so I'll leave the x alone. Derivative of cosine is negative sine of x. Plus, take the derivative of x, that's 1. Leave cosine alone, so that's cosine of x. Derivative of sine is cosine. I'm not applying L'Hopital's rule again. I'm just trying to algebraically clean up this output after taking the derivatives again. So I have sine of x up here. And I have that's all over. Cosine of x plus cosine of x is 2 cosine of x minus x times sine of x. So when I put 0 into the top here, sine of 0 is 0. All that over 2 times cosine of 0 is 1, so that'll be 2 minus 0, sine of 0 is 0. So it turns into that. So this is equal to 0 over 2. That's not indeterminate form anymore. 0 divided by 2 is just 0, so we get 0 back for our limit on that one. Okay, so the final one from this block that we're going to look at is going to be this example here, where we want to say what is the limit as x approaches 0 from the right of x to the x. So if we plug in, we get 0 to the 0 power, which is indeterminate. So what we're gonna need to start trying to do is start trying to get this in the form 0 over 0 or infinities over infinities somehow. What we're gonna use is, if I have x to the x like that, I'm able to rewrite that as e to the natural log of x to the x. So if you have e to the natural log of some value, we'll call it a, e and the natural log will undo each other, and that'll just be a. So we're going to use that property. So if I start with a x to the x, I can let x to the x be like the a. Then that's the same as e to the natural log of x to the x. Now that this is inside a logarithm, the x power here can pull out front. And what we'll get, we can let the limit drift up across the e. We'll get limit as x approaches 0 of x natural log of x, which still isn't quite the correct form, but we're going to use that trick we used where x, we can push it downstairs and write it to the -1. So we get e limit as x approaches 0 from the right of natural log of x over x to the -1. We're going to ignore that this whole thing's raised to the e for a moment, and we're just going to focus on the limit part of this. So again, we're going to kind of just kind of focus on that. So we'll say, how do we do that? As 0 goes to the, as x gets close to 0 from the right of natural log of x, that's going to go off to -infinity. As 0 goes to the right of x to the -1, that goes to +infinity. So we're in form infinity over infinity. So we're going to have e to the limit as x approaches 0 to the right. Derivative of natural log of x is x to the -1. That's over -x to the -2. You're able to reduce that fraction down. So we'll get x to the -1, all that over -x. Sorry. We're able to reduce, since this is an x to the -1 up here and that's an x to the -2 down there, we're able to let the x to the -1s cancel. So that'll leave 1 up top. That'll leave us a -x to the -1 down there. I'm able to rewrite this. 1 over x to the -1 is the same as x, and this negative sign will say that this is the same as -x. So this will be the same as e to the 0, which will be the same as 1, and we are done there.